We present EgoForce, a novel approach for estimating the camera space position and pose of hands from monocular egocentric RGB inputs. In this work, we estimate how the hand is posed and where it is in 3D relative to the wearer's head-mounted device, using only a single camera. In this example, the G and A are behind R. They are then grabbed and pulled into line, showing our robust 3D position tracking. EgoForce provides real-time pose updates with accurate articulation and precise 3D localization. A straightforward way to extend state-of-the-art root-relative hand pose methods is to combine them with depth estimators to lift their predictions into camera space. However, existing depth estimators fail to provide millimeter-accurate depth for hands. Another line of work adopts a second-stage optimization, where they estimate 2D to 3D correspondences between detected 2D key points and projected 3D hand poses via iterative fitting at test time. However, these methods are slow and sensitive to noise and initialization. Recently, methods like Hand DGP have unified 3D hand pose estimation and camera space 3D, 2D correspondence matching within a neural network framework. Nevertheless, their accuracy still lags behind root-relative approaches. They are sensitive to camera optics and FOV variations, and they suffer from significant monocular scale depth ambiguity. Methods such as Dynahamer and Howar couple SLAM with root-relative hand pose to estimate the camera pose and reconstruct the global hand trajectory. In contrast, we directly regress camera space pose using the native camera model. Moreover, these pipelines are computationally expensive and typically assume an ideal pinhole camera. Given these limitations of prior work, our objectives are threefold. Achieve accurate camera space 3D hand pose with high articulation accuracy and precise hand localization. Robustly handle diverse camera optics, including wide FOV and fisheye lenses, as well as extreme perspective changes. Reduce depth scale ambiguity and stabilize camera space hand pose, even under heavy occlusion. We compare our method against state-of-the-art approaches on three challenging egocentric datasets, Hot 3D, Arctic, and H2O, and showcase consistently superior performance in both pose and localization accuracy. On the Hot 3D dataset, the extreme fisheye distortion of the lens means that rectifying the image while preserving the same visual coverage introduces strong skewing near the image borders, causing previous methods to fail. Here, we observe that our estimates are more temporally stable and align more closely with the ground truth data than those of competing methods. The H2O dataset uses an ideal pinhole camera with pre-rectified images of hand-object interactions. Even here, our method outperforms competing methods and provides a more faithful reconstruction of the hands. Similar to Hot 3D, we observe that our estimates are more stable and align better with the ground truth, demonstrating that our method generalizes well to both fisheye and pinhole camera configurations. The Arctic dataset uses an egocentric pinhole camera with strong radial distortion and includes heavy occlusions from hand-object and hand-hand interactions. Even in this challenging setting, our method remains robust and produces accurate estimates, as the arm prior anchors the hand under severe occlusions. Similar to the previous evaluations, we observe that our estimates are more stable and better match the ground truth. Overall, these experiments demonstrate that our method handles occlusions and complex hand motions well and generalizes across a wide range of egocentric camera setups. Compared to Hand DGP, the prior state-of-the-art for camera space hand pose estimation, our method yields much smoother, temporally stable outputs with negligible jitter. Accurate trajectories with minimal jitter tell us if a method can reliably estimate stable hand motion during complex interactions. We observe that our method produces smoother wrist joint trajectories than the competing approach. Even when the hand joints are heavily occluded by objects during complex motions, our method still recovers reasonably accurate trajectories. Our method is able to reconstruct plausible forearm geometry even when the forearms are heavily occluded from the egocentric viewpoint. Our method produces accurate 2D projections of the hand meshes even under extreme distortion, which is common in egocentric capture devices that aim to cover a large field of view within a small form factor. Even under extreme occlusions, where the hands are almost completely occluded, our method produces plausible hand poses by leveraging the forearm prior to anchor the hand. Even with motion blur from fast movements, our method stays robust and can still capture fine hand articulation, like picking up a snack chip. We also showcase mesh projections on the HO3D dataset, a dataset recorded from a third-person camera for completeness. Next, we visualize the projected hand and arm meshes. Note that the forearm meshes are not always pixel perfectly aligned, as they primarily serve as a regularizer that anchors the hand in camera space and mitigates scale depth ambiguity. Nevertheless, we still obtain good arm projections, and refining the arm modeling remains an interesting avenue for future work. Our method can operate effectively without arm input, functioning as a standalone hand pose estimator. However, incorporating the arm significantly improves hand pose accuracy, especially under extreme occlusions. By incorporating a variational arm prior, our framework provides plausible arm reconstructions, even when the forearm is missing from the input due to occlusion, a situation frequently encountered in egocentric recordings. This can be observed in frames where no arm ground truth is present, with ground truth shown in white. We observe that removing distortion from the crops yields the largest gain in localization accuracy. On top of this, injecting camera geometry into the network via the crop intrinsics token further improves localization, especially near the highly distorted periphery of the fisheye lenses. Adding a Kalman filter to smooth the recovered translation from the race-based solver not only reduces jitter but also improves localization accuracy. Please refer to the paper for more details. By estimating the camera intrinsics with tools like AnyCalib, our approach can be applied to egocentric footage captured by devices for which no calibration data is available. Even in this setting, our method accurately reconstructs hand poses. In this example, the interhand distance is well preserved, and the reprojected 2D joints closely match the observed hand joints. In summary, we present EgoForce, a framework for accurate camera space hand pose estimation in egocentric settings. It uses the forearm to anchor the hand and mitigate depth scale ambiguity. And by evaluating across datasets with diverse camera optics, we show that EgoForce generalizes well to many different egocentric camera configurations. Thank you for watching.